Okay, now we are going to do exercise 1.1 of Ncert. Exercise 1.1. Question number 1. Determine whether each of the following relation is reflexive, symmetric and transitive. So basically what we need to check whether the given relation on the given defined set is equivalence or not. So part A, what does it have? A set. Obviously we need a set 1, 2, 3, 13 and 14. Finite set. Relation R is being defined as x comma y such that xy should satisfy the given equation. So first we need to find out which elements satisfy this equation. This can be basically written as 3y 3x equals to y. From this I can write this. It makes it a little bit simpler to see which elements satisfy this condition. Now R is nothing but choose x equals to 1. What it will give? Y equals to 3. They will satisfy the condition. Choose x equals to 2 here now. Y will be 6, x3, y9, x4, y12, and for x equals to 5 we will get y equals to 15. That is not an element of R because 15 does not belongs to A. So this is my relation R. Now reflexive. Is it reflexive or not? This is not reflexive. Why? Because definition of reflexive says that for every element A in the set A, like 1, 2, 3, for all of these elements the regular pair A comma A must belong to R. But this is not so because 1 comma 1 does not belongs to R. Similarly 2 comma 2, 3 comma 3, none of the regular pair belongs to R, so this is not reflexive. Now symmetric. What does symmetry say? That if we have a pair A comma B in R, then the symmetric pair B comma A should also be in the relation R. Okay. Now 1 3 is visible in R, but 3 1 is not visible in R. Clear? 1 comma 3 belongs to R, but 3 comma 1 does not belongs to R. Thus this is not symmetric. See, this should happen with every pair. Suppose that if we have 3 1 in this relation, then we will check for 2 6. 2 6 is there, then 6 2 should also be there. If 3 9 is there, then 9 3 should also be there. None of the pairs should be left. Okay. Now transitiveness. What does this say? If A comma B belongs to R and B comma C belongs to R, then A comma C should belongs to R. Let us choose this is my AB, then I am bound to choose this as my BC because second coordinate in first element should become first coordinate in the second element. So 1 3 3 9 is now my AB and BC. But 1 9 does not belongs to R. This makes that the relation R is not transitive anymore. Okay. Now part B of this question. What does it say? Now my set in which I have to work is the set of all natural numbers. that is 1, 2, 3 up to 4, and the relation R is being defined as coordinate pair x comma y such that y equals to x plus 5 where x is less than 4. See, x is strictly less than 4. This is a set builder form. Now I am going to make R in elementary form, that I will list the elements. Y will be equals to x. Y will be equals to x plus 5. Okay, and x is strictly less than 4. Now the lower bound will be what? Because x belongs to set of natural number. Yeah, also y also belongs to the set of natural number, because both of these elements are from the set, parent set, in which we are finding the relation. Okay, now relation, this will be when x equals to 1, y will be equals to 6. When x equals to 2, y will be 7. When x equals to 3, y will be 8. Observe, x started from 1 and goes to 3 because this is strictly less than 4. So 1, 2, 3, these are the only values which x can assume. Means x can either be equals to 1 or 2 or 3. Clear? Okay, if we add on to this question, we can see that R is neither reflexive, because 1, 1, 2, 2, 3, 3, nothing is there. So R is not reflexive. Just one reason is sufficient. 1, 1 does not belongs to R, since 1 is an element of the set. So 1, 1 should belong to R in order to make it reflexive, but 1, 1 does not belongs to R. Thus, this is not reflexive. This is not symmetric as well. 1, 6 belongs to R, but 6, 1 does not belongs to R. Transitive. This is, we can't even talk about the transitiveness here, because for that we need A, B. This is my transitive definition. A, B belongs to R and B, C belongs to R, then A, C should belongs to R. So I cannot find any AB or BC corresponding to that. So in that case, what will I say? We'll simply say that R is not transitive, because we cannot find any two pairs AB, BC, so that my AC belongs to R. So R is not transitive. So here also R is neither symmetric, nor transitive, nor reflexive also. Okay, now moving to the next part of this question. What does it say? The set A is given as 1, 2, 3, 4, 5, 6. A equals to, this is my part C, 1, 2, 3, 4, 5, 6. And the relation R is being defined as what? Ordered pair xy such that y is divisible by x, means the second element should be divisible by the first element. Okay, so every number is divisible by 1, so clearly I can write 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Here, so now comes to 2. When x equals to 2, only possible TR 2, 4. Yes, 2, 2 also will be there, and 2, 6, and about 3 will be 3, 3, and 3, 6. Okay, now the possibilities about 3 are done. Okay, about 4, 4, 4, 5 5 6 6. These are all the elements. I have listed them. Now we need to check whether my given relation R is reflexive, symmetric or transitive or not. Now since I can find my regular pairs in it, because every number is divisible by itself, so when x and y both are equals to each other, then 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 will belong to this relation R, which makes it reflexive. R is reflexive. Remember how to solve the question. We only need to know about R. What will be my R? This is my R. Now I can find out whether it is reflexive, symmetric or transitive. Like about symmetric, what do we have? Do we have 2, 1? No, because 1 divides 2 and 2 does not divide 1. So about symmetry, we can give example. That it is not symmetric because 1, 2 belongs to R, but 2, 1 does not belongs to R. So this is not symmetric. This makes it not symmetric. About transitiveness, what do we have about transitiveness? Let's see. Now because number of elements are quite more, so I cannot go by elements. Like if I choose 1, then I choose 1 2, then I will find 1 2 is there or not. Now if I have 1 2, then 2 4, then I'll see 1 4 is there. I cannot check all these numbers like this one by one, so we will use the general pattern. Condition: let A, B belongs to R and B, C belongs to R. Condition to be in R is what? That A divides B and B divides C. Y is divisible by X is same as saying that X divides Y. So A divides B. This means I can write my B as some number n into A, because if B is divisible by A, then in a multiple of A, table of A, I'll definitely get B at some number, and similarly I can write here that my C equals to B, M. Now I just need to check whether A, C belongs to R or not, and for that I have to show that A divides C, means C is equal to A into some number. Now what will be this number? I can find this from here. Observe that C equals to BM, B cross M. This is my observation. But what is my B? My B equals to A cross N. So I can use this value here for B. Then I'll get C equals to A cross N cross M, which will be equals to A into N cross M. This shows that C is divisible by A. Therefore, for any arbitrary pair A, B in R and B, C in the relation R, I'll definitely have my A, C in R, which makes the relation transitive. Thus I can say R is what? Transitive. Now we'll see part 4 of this question. Part 4. Now what does it say? Now we'll observe this part 4 on set of integers as well as on the set of natural numbers, so that we can see how does the parent set makes a difference on the relationship. R will be my same. It would be is an integer, or R equals to same set but x minus y is a natural number. Now here any number minus any number, subtract any two numbers, I'll definitely get an integer. So I guess this is some kind of universal relation here. Because for any two numbers we subtract, because x comma y are from the set of integers, and if we subtract any two integers, this will always be integers. So this makes that for any arbitrary pair I'll choose from a cross a, that will definitely belongs to R, because any x comma y in the product set a cross a will give me x minus 5 equals to some integer, which is the required condition to be a part of this relation. So this will send this xy in the relation R. This ultimately means that a cross a is subset of R, but by definition R is subset of a cross a. This gives me that R equals to a cross a, and that is why I have written that R is nothing but a universal relation. On the other hand, is this a universal relation? No. Answer is no. This is not a universal relation. Yeah, here I can say being a universal relation is always an equivalence relation. So I don't need to check. If I write something is universal relation, then I don't need to check whether it is reflexive, symmetric, transitive or not, because universal is equivalence. Yeah, equivalence may not be universal. See, universal implies equivalence. I have this example, but equivalence does not imply universal. This condition can be used in many exams, 1 marks exams, like we have some questions in IIT. Okay, now coming to this is an additional part we have created for our own. Is this a universal relation? No, because if I choose 1 comma 2 from R, then 1 minus 2 will be minus 1, which is not a natural number. So this pair does not belongs to R. That means what? This pair is in, these are my sets, I have chosen these as A. Of course this is in A cross A for the set of natural numbers, A equals to set of natural numbers, but this is not in R. So this cannot be a universal relation. This element is here, but 1 comma 2 does not belongs to R. Here also I tried to choose 1 comma 2, but later I get contradiction that this is not possible. So this is not universal relation. Now you can check whether it is transitive, symmetric, reflexive or not. This is a question. We can do it in the same way like we have done previous questions.